All right, so I'll make the introduction and then Shihao, you're going to take it over. So here today we have Dr. Shihao Yang. Shihao is one of my colleagues at in the School of Industrial System Engineering at Georgia Tech. Before he joined Georgia Tech, that was about 2 years ago, right?
Yep.
He was a postdoc in Biomedical Informatics at Harvard Medical School after he finished actually his Ph.D. in statistics from Harvard University. Shihao's research focuses on data science for healthcare and physics, with the special focus on electronic health records, causal inference, and dynamic system inverse problems. Let's try Shihao to take it over from here.
Thank you, Nicoletta, for the very good introduction, and thank you for inviting me here to give a talk. Today, I'll talk about my joint work with Stephen and with Nicoletta on a model for causal inference model, propensity score model for on the electronic health records data, and with a special case study or application in the diabetes diagnosed youth and young adults. This is still a work in progress. As you will see, I will honestly, outline a few challenges that we saw along the way and some ideas to address it, but still it is a work in progress. And the organization of this talk will be, I will talk about in the general setting a little bit on the EHR and on the causal inference propensity score model, and in fact, our new method proposed. And we'll talk about simulation results. And then finally, I'll move to a real world application of the diabetes data on Medicaid. And that part is still very heavy, currently under development. So let's get into it. All right. I think everyone now is very familiar with the electronic health records. This is just an animation of how this data works and how it is actually collected. We have a patient here that, whenever patient visits really a hospital, regardless of it's A or B, those data get stored in the medical EMR platform. And this platform is really an integrated storage hubs for basic demographics. And every time you go to go to lab results, examination records, and you have the hospital visits. Every time you go to a hospital, you have a visit. And also you have some personal health records from it. And the family member, physicians, and insurance company can access it. And this is general schematics of the EHR data. In particular, in this talk, we will focus primarily on the insurance company's perspective, how insurance see this data, and we actually get access to this EMR data through the lens of insurance company. That's why we will assume we do not have a physician's note, doctor's note for this data, but what we will have is the the diagnosis code, the billing code, this procedure code for each particular patient. Keep the Medicaid data in the back of your mind when I talk about my models. So that's EHR, and that's the data. What's the question that we're trying to ask? All right. Well, this is another schematic overview of how the data look like. I talk about, is through the lens of insurance company, and that's why the three most important codes for us will be kind of ICD codes in the diagnosis. We have some medications, NDC, national drug codes, and the procedure called CPT, right? Sometimes we also have vital results and lab results, okay? And this is ordered really in a very tall table sense, okay? You have one patient, you have another patient, you have another patient, you have another patient. Each patient have a lot of records. For example, right, the patient I have here, the records might span through from 2000 all the way to 2005. In this particular case, a 5-year record. We have a database that spans out the 14 years records. So it was really a tall table where each patient have multiple entries, many entries in the same EHR records table. What we also have is a demographics information, right? For each patient is one single row, okay? And we have information such as gender and zip code. Sometimes we also have birth year. You get the sense. Those are static variables that we get kind of stored for each particular patient. That's kind of demographics data. So in general, we assume we'll have access to these two tables, and the rest of the data is basically derived from these two tables. And electronic health record, EHR, provides a very good opportunities, for me as a statistician to look at the real effect of a, let's say, new treatment procedure or a new drug in the real world, right? Typically, what we have in the gold standard is randomized control trials, RCT, or also called randomized clinical trials, RCTs, to evaluate really in a very clean lab settings. You have sophisticated enrollment criteria. We look at a couple of hundreds of patients, already very expensive, and we establish the efficacy of a drug, and FDA approve it, and now general public can use it in the real world setting. And oftentimes we kind of observe there's a difference in the real world setting efficacy of a drug than the lab setting. And that's what the EHR, electronic health records, this type of real world data provides an opportunity, right? For example, this is my red table for each patient, right? I get the red table from my green table. The red table is an extraction from the green table where I find out the particular treatment assignment of interest. It can be a new drug, it can be a new medications, right? I look through the records, find it, and put the treatment assignment here. 0 is the conventional treatment, 1 is the let's say the new treatment. And then I measure a type of outcome, also derived from this table. It may be some for example, binary outcome, so continuous outcome, a value of specific lab measurements, observed after the treatment. Other possible outcome of interest will be, for example, survival. Some of the data might have survival. Medicaid, unfortunately, doesn't have it. So, but mortality is definitely one variable of interest. And there will occurrence of a specific disease or condition. For example, we're looking at side effect of a particular treatment. That will be another binary type of outcome, or another type of outcome will be time to event, time until what happens, etc., etc. So the general question being asked, from this two original raw table and one derived table of treatment outcome is, can we use this data to study the treatment effect of a new medication? Can we do causal inference on the EHR? That's the general question of interest to me. All right, so to answer that question, we first need to formally define what do we mean by causal inference, right? And obviously, causal inference in the more traditional, in the classic setting, talks about in an experiment, right? You have two patients roughly looking the similar. Ideally, they are twins. You give one of them a blue pill, the other one a red pill, and look at the outcome. In our case, we are dealing with something called observational study. That is, the data, there's no experimental design. All right, we do not submit a proposal for experiment first and then conduct the experiment according to the proposal. No, the data is collected a priori beforehand. And so this is in general called observational study. We are trying to derive something with a causal interpretation from a data that is kind of collected already. And in general, this is very difficult. This is possible, but difficult to do. And also, we need to pay attention to the specific detail, which I will talk about later. There are two schools of thoughts, mathematical framework. That's, basically what is cause and what is the effect. There are two schools of thoughts that is currently prevailing and most popular. One of them is a potential outcome framework. It's also called the counterfactual framework, or Neyman and Rubin causal models. And the other one is called the causal diagram framework, which is now more popular in the machine learning. The two really have their own kind of advantage and disadvantage. But because we are right now looking at the medical data and the vast majority of causal inference in the medical domain focus on the potential outcome framework, and that will be the framework that we will adopt as well. So what is a potential outcome framework? Let me give you probably a 5 minutes background review for the potential outcome framework, especially for those who are not super familiar with it. I think this setup is kind of different from the usual regression that we run, and I want to be super clear. And for those already familiar with the subjects, still it's good to refresh a little bit. The basic setup: unit is a person or place or thing upon this observation, right? It's my index by I, right? So the treatment is operated on this unit. In our case, each unit is a patient. That's why you see I'm introducing a new table, okay? This yellow table, where each patient is one row, okay? And each patient is a row. Oh, what is all of this information? These informations are covariates, right? Patient characteristics of each patient. In particular, they are usually denoted by X, right? This is my X1 patient, X2, this is my XI. And the first column, right? This one is my X11. Is this patient have a disease A in the past 5 years, for example? All right, I'm just trying to give you an idea. This one is X12. The second feature or second covariance of patient 1 is disease B. The patient have a disease B in the past 5 years. There could be some vital signs that is in continuous. So this is like X1M. There will also be, static variables like sex and zip codes of a patient, X1N minus 1, X1N, for example. All right. Typically, we use P, sorry. So these are all my features, P covariance. What is my treatment? My treatment assignment is right here. You either get treated or get control. 0 usually means a control, 1 means a treated. So my patient 2 is treated, my patient 1 is a control patient. Same as my patient I is a treated, my patient I plus 1 is a control patient. The last one is really where the potential outcome framework from the notation, even starting from a notation perspective, differs from a regression. You will have outcome. Usually we have outcome, right? We call this Y, Y1, Y2, YI plus 1. That's it. But in the potential outcome framework, we're actually talking about outcome under treatment and outcome under control. What's that saying? Think about the experiments. Think about the RCT counterpart as well. If you were patient I, you actually have 2 YI. Right? YI1 is the outcome if you were given the treatment, and YI0 is the outcome if you were given the control. And the difference between these two is really the causal effect. So really, the potential outcome framework invents to augment the notation. To be, it's not about in the regression framework, John gets a drug, Mike get a placebo, and take the difference between John and Mike's outcome. No, it's about if John get the drug, if also John get the placebo, what's the difference in the effect for John in specific, right? And that notation and open up, that's why it's called potential outcome. It's something that you potentially could have, right? Potentially you have a treatment or potentially you have a control. Schematically, what it does is transfer the upper panel that I have here into the lower panel in the potential outcome framework. In particular, all right, we're talking about the outcome part transform right here. This is the transformation that potential outcome use and particularly points out. All right, so let's say the patient one, there will be a patient one under treatment, under control, and patient one outcome under treatment. But because patient one received control, we only observe the patient one's control outcome. What's the patient one's treatment outcome? We don't know. For patient two, because patient two only received the treatment, we only observe patient two's outcome under the treatment. Was the patient two's outcome under control? We also don't know. All right. So indeed, the potential outcome framework augments the variables, but it leaves a huge missing data problem. But this missing data problem, once we frame this problem, there are ways to deal with this problem. And in particular, we can look at assumptions that kind of think about it as becomes a missing data imputation. We can fill out those values. And if those values are filled out somehow using the model and approximate it, we can subsequently get the causal effect. Right. So there are talking about models, right? There are assumptions in place. And so one of the assumptions is the stable unit treatment variable assumptions. So essentially it talks about no interference among units. That is, John's results, whether get the treatment or control, doesn't depend on whether Mike gets the placebo or the drug. All right, so there's no spillover. There are certain cases where this one is assumption is violated, for example, using on a graphical network, but our conventional case, we don't consider that. And there will be a single unit version of the treatment available. For the simplest way to put it is that there is no dosage in this. I have assumptions. And there's also technical assumptions. We talk about, okay, even the covariates X, remember all of this are my covariates. Each patient is one row in my covariates. So there are frameworks that states that if we can have that given the covariates, the treatment potential outcomes is independent of the treatment assignment, there are ways that we can do the modelings. What's the intuition here? The intuition is saying that there is no hidden confounder. All right. What do I mean by hidden confounder? For example, one of the hidden confounder, well, in the old days, let's say my outcome is whether you are having a lung cancer or no. And my treatment assignment is whether you're bringing a match. All right. And one of my XI should be that whether you're a smoker or not. All right. If you are a smoker, then your treatment outcome, all right, smoker or no, doesn't care if you are bringing a lighter or a match with you. Your lung cancer outcome is independent once you know the information of covariates of being a smoker. But if without a smoker in the conditioning part, right, you are missing an important covariates. What will happen is that you can mistakenly identify that there is some marginal relationship between whether you're bringing a match or a lighter with you to your outcome in the cancer. Overlap is another technical considerations, is really essentially talking about, if there is a drug, let me put it this way, there should be overlap in the treatment population and control population. For example, if there is a drug that is only available for female, then it doesn't make sense for us to evaluate the efficacy of this drug in the comparing in the male or comparing to the female, right? So that is, if female always get treatment and male always get control, then there is no point to do the causal inference. There is no counterfactual at all, right? So the same as, in the counterfactual or potential outcome framework, the thing that we are trying to evaluate should always exist a hypothetical scenario. What if the world is what if you receive a treatment versus control? So having like all of that, let me finish this potential outcome framework review. already talked about, once we know the Y0 and Y1, the treatment effect is really just the Y0, the difference between these two, right? If I minus this, minus this, minus this, I get the individual treatment effect on the individual level. And if let's say I get a difference, right? I get some value here, some value here, some value here. And if I sum them up or take the average, this is my AT average treatment effect. Very simple. Just compare single person's treatment effect, average of those get average treatment effect. Now, it is obvious what's the elephant in the room. The elephant in the room is that I don't know what are those question marks, right? Those are missing values. We only observe one of the pair, Y0 and Y1, and the other part is completely missing. And that's the fundamental problem of the causal inference. And under some assumptions, we can compare observed distributions Y under treatment and control if covariates are balanced. For example, if the covariates, if you have right amount, if the covariates, and the treatment control, you basically adjust, right? Try to think about it as we are trying to find the person. John is assigned a treatment. We try to find by matching or weighting John, find another Mike that might be, is a control patient who looks roughly the same as John. That's kind of the intuition behind. Due to the lack of randomization, right? So we have to find or having some, what do we mean by similar, right? We are looking at covariates, looking at treatment assignments in observational studies, can be confounded by the individual level characteristics, and some characteristics are common cause of both treatment control, common cause for both the treatment assignment and outcome, and that can create confusion of the causal relationship. So indeed, what I'm trying to do is we're trying to find patients that are similar, and essentially we are doing the control for confounding. All right. So having said all of that, is this problem framework already solved? Well, now I'm getting rid of the yellow table. As you can see, in the raw EHR data, the fundamental problem or the fundamental one of the fundamental difficulty is that we don't have that yellow table that where each patient is a row. The covariance data we need to balance is no longer in a simple form that I have a feature and I have I as my study subject, my unit, and I have a nice table layout. Rather, it's each patient's raw EHR, right? All of this is my X1. Previously, my X1 is just one row. All of this is my XI. So in light of that, my X1 to XI can be tables of different length, right? How do I control for the variables X1 all the way to XP? Okay. So let's look at the existing problem. How do people do this? If our existing method only works for a yellow table, then the existing method really says that, okay, all we need to do is transform this green table into the yellow table, right? So existing confounding control methods really require, I call it step featureization, all right? Think about it as from all of 5 years records of patient I, really featureize and condense it into the one single row of I, right? Obviously, I also identify the single row here and concatenate on top of it. So in this step, what I'm doing, I'm effectively summarizing my raw data into a table where each column is features. That's what I call featureization, right? For those who are familiar or have ever have some experience with EHR data, this shouldn't find surprising. This is actually the part we probably spent 80%, not if not 90% of our efforts in, right? And often in this step, we need to team up with a domain expert, ideally a clinician, to really find the feature that is most relevant for the inference task that is of interest, right? So the raw EHRs are high dimensional, right? Think about a tall table, all of this. And sparse, even if we're looking at the medication code, we're looking at the procedure code, right? We're looking at the diagnosis code. Those dictionaries are very, very long. But what actually appears in this particular patient can be very small. So what you could have is you have a lot of zero in your feature space, because for those particular conditions, this patient doesn't really have, right? The featureization is a painful and complex part. Think about it. Question asked include, do you have disease A in the past 5 years? Do you have disease A in the past 3 years? Well, do you ever have disease A? Now I'll talk about A. How about disease B? How about disease C and D? All right. If you have disease A, have you ever had a particular type of treatment that may affect your subsequent that may have a side effect or affect your subsequent treatment assignment? So really, ideally, this step of featureization is mimicking, when a patient go to see a doctor, what the doctor is mapping this patient in the back of their mind, right? Think about as doctors, physicians evaluating a patient. So that's really the featureization I'm referring to. And this can be a long table, and sometimes even the doctor wouldn't be able to articulate exactly how long it could be. It could easily be very, very long. But remember I said for causal inference that one of the key assumptions is that you cannot have a hidden feature, meaning that you have to summarize all information that might be relevant to both treatment assignment and control. So basically, you have to have all possible potential confounding variables in this yellow table. So oftentimes we just grow the yellow table to be more and more features, right? So I call this a tall table. Each patient have a very, very long records into here a fact table, right? A table that have very, very much a lot of features, a lot of columns, right? From a tall one into a fat one is a featureization, and it is important and is also very subjective. Okay, so after the featureization, we're not done yet, right? What's the usual causal inference framework next? Well, after featureization, we really have a wide variety of tools that is available to us. And one of the most popular one is called propensity score. And propensity score really is this kind of summary statistics. One scalar summary statistics of all the covariates, which have the interpretation of probability of getting the treated, getting the treatment, right? Getting the drug rather than the placebo. And it's been proven in the literature, very, very old papers talking about this propensity score naturally balance the distribution of all covariates in the treatment groups. Treatment assignments and the covariates are independent of each other, controlling this propensity score. And also another key property is that if the treatment assignment is unconfounded given the X, then the treatment assignment is unconfounded given the propensity score. Really, this talk about, okay, if I can have unconfoundedness with the entire set of my feature, all I need to control is this scalar value of the propensity score. So this obviously is very nice. Think about previously you are stratifying, right? Think about conditioning as stratification. You're stratifying by age, gender, birth year, and past illness if you have a disease A, disease B, so on and so forth. Now all we need to do is to summarize this X using the propensity score and only stratify by the propensity score And the theory tells us that it will be enough to unconfound the entire observational study. So those two theoretical properties of the propensity score really make an essential piece of the replicating or making the observational study as close as to the randomized clinical trial, randomized control trial, RCT, as much as possible, so that it's actually in the central piece of obtaining unbiased treatment effect estimates in the causal inference. Okay, so propensity score methods, summarizing how we are actually doing it. We're operating it really in three steps. The step one is featureization. There are some guidelines in the guide. There are some guidelines in using the propensity score. In featureizing the raw data into this syllabic covariance. This FAT table I talked about, and then from here, this table, we're able to build a treatment assignment probability. Train a model EX. One of the most widely used classical tool is logistic regression, for example. And from here, we can use, estimate average treatment effect either by stratification, can be matching or weighting, and to get the kind of individual treatment effect estimates, and then we can get the population average treatment effect estimates. So really, here are the three steps we often use to obtain the inference. Step one, featureization. Step two, model. And step three is the causal effect estimate. 3 steps. And as I outlined the procedure of the typical workflow on the EHR, you probably already realize, the step one and step two. Step one in particular is very painful, and step two also have some subjective component in how do you build the propensity score model. Is that going to be a logistic regression? Is that going to be a more machine learning like approach, like a tree-based model? Some people actually use boosting or random forest, right? There are a lot of selections over there, flexibility in step two as well. So, and also the step three and both step three and step two have this dependency of the step one. Like I keep saying, if you fail to select one of the important confounders into the data, there's nothing we can do. From the it violates the assumption, subsequent causal inference assumptions, there will be bias, and there's very little we can do in the step two and step three for the correction. There's something we can do to make it doubly robust, for example, but requires a lot more effort and still is not ideal. So what is our goal here? Our goal is, if the step one featureization is so sensitive and so time consuming, so subjective, so much rely on the clinician or domain expert, our question is, can we address all the challenge in the step one by using the raw data completely? Can we our goal is to bypass step one, or in another way, we address the separation between step one and step two. Can I have one single step, a unified propensity score model to bundle step one, step two together, so that I don't have to have a featureization step? Graphically, this is what we are trying to do. Okay, we want to remove the featureization. We don't want to use the this yellow table anymore. We want is from the green table and blue table directly model the propensity score. And from the model, I have step three, either by stratification, matching, or weighting from the propensity score for my treatment outcome estimation. That is our goal. Okay, and before I go to my methods, and I spend a lot of time deriving why we are doing this and what we are trying to do. Any questions so far?
Hi, this is Lisa Simas. Can you hear me?
Yes.
Okay, good. I was just wondering, based on the premise of kind of being able to predict in the same person, the counterfactual, I guess.
Yep.
Just wondering, how does a crossover so I guess it's almost as if you're designing a crossover trial, but without the data. Is that kind of the idea?
No, you still have data. You still have this entire yellow table. Kind of, the idea is, predict someone's treatment assignment, and the outcome is like, you're trying to look at all similar person for John. Let's say I make a John Doe, right? All similar persons to John, and look at subsetting all those similar persons to John who received the control, which John didn't receive. And look at all of those patients' outcome and trying to get a model of using those information to predict what if John receive a placebo, what will John's outcome be?
Yeah, okay, I understand that. Okay, yeah, I was just thinking about how, given the effect that you're observing, in this case, you're only observing one thing, but in a crossover trial, which clearly this is for observational non-experimental data. But in that setting, the goal would be to derive, both of those effects. So I could see how the utility of having a crossover trial, how this is a very interesting approach to do the same in some ways, hypothetically, I guess.
Yes.
But without actually having experimentation.
No.
So this is really neat. Just wondering also about you mentioned that the featurization process can take like 9% of the effort.
Yeah.
So I don't know, in your experience, is it pretty easy to mess up in that process because it's so it could be so exhaustive?
Yeah, it could be so exhaustive, and it could be a back and forth between me and my reviewer, because the reviewer always asks, have you considered this? Have you considered that? Why don't you consider this? And the list of my table, the columns of my table just grow longer and longer. And also, there will be different clinicians I consulted, and sometimes is a little bit of subjective, right? Think about a feature will be, have you had disease A over the past 5 years? Why 5 years? Now, okay, I have another feature called whether you have a disease A in the past 3 years, hopefully to make it less sensitive. And it's just a back and forth kind of data feature engineering process that requires domain knowledge, and sometimes subjective between different people may have different view. And for me to be more conservative, like I need to put everybody's input into my yellow table.
Yeah, very interesting. Okay, thank you.
Yeah. Okay, so indeed, I want to bypass that. So what I want to do is, okay, can I directly use the raw data right here to build a model so that I can 100% guarantee that all information that I had at my hand will be used to model my propensity score, so that for my subsequent causal inference. So that's my goal. And to do that, I'm going to introduce a bit of our method. So let me go to this slide first. Okay, so this is a kind of machine learning schematics. Let's do not be intimidated about that, right? So think about it. Previously, I have each patient as one row, xi, as one particular row in the data set. Now my xi is just right here, a table. So my xi actually have 3 indices now. My xi, now you see that move my I from the subscript to the superscript towards the right. So that means, for each patient I have his first visit to the hospital all the way to DI's visit to the hospital. So indeed, I still have the rest of my framework. Don't look at the top for now. Let's look at let's focus right here first. Okay, the ZI is still going to be treatment assignments, right? So even if I have a clinical long observational study data sets, towards the end, I still observe, okay, real world study is this patient on a particular drug, on drug A or drug B, type of treatment A or treatment B. And I still have my potential outcome of, if you are on treatment, what's the outcome? If you have control, what's the outcome? The only difference, the major difference, the only but very major difference is previously I have my XI. a very nice row of data. Now I'm more talking about, my X superscript I, that is a different rows of data. Each xi can be a vector. And also I have static information like the birth year, the gender, the zip code associated. So mathematically speaking, what I'm trying to do is to build a model that depends on the entire, data of sequence data, xi1, xy2, all the way to xidi, together with the demographic variable. That is a propensity score. So basically, I try to derive this property. The probability of treatment assignment equals to 1, conditioning or having all your feature of all your past available electronic health record. I want to give analogy, before getting intimidated about what it is and why it inspired my method, right? I think about what? I think about each patient's EHR as a book. It's a sequence data, at the end of the day, if I just toss all my medical knowledge about it, I am reading a booklet of this patient, right? It's a sequence data, it's labeled by date. And some patient might have a thicker booklet, some patient have a thinner booklet, it have a different length. And, it's really a vocabulary. Just, usually I read English. Now I'm not only reading English, I'm reading code, ICD code or CPT code or NDC code. So really, that's it. It's a booklet not written in English, but written in terms of coded variables. And for me, especially with the recent advancement in the natural language processing, it looks like, okay, machine doesn't care whether it's in English or is written in terms of ICD, CPT, right? If I were to have a machine learning algorithm directly apply to kind of digest this booklet of encoded variables like ICD or CPT codes, would it be able to tell me a single probability of the probability or the single propensity score, which have the interpretation of probability of getting treated, given the entire information of the EHR? And that's indeed our idea. And we look at, okay, what's the current state of art? Natural language processing, we kind of all know right now that there's a breakthrough in the natural language processing models. We use attention-based mechanism. And that's what you see up here. This is really just a attention-based mechanism. What I feel like, I'll tell you what, it schematically, it's like I treat each row here as one sentence in the natural language processing. And then through my sentence into the current natural language processing model, so that basically I threw a paragraph, sometimes longer paragraph, sometimes shorter paragraph. And I asked the natural language processing to give me an output that basically summarizes this patient, one single scalar that summarizes this patient. Think about this as this way. And modelly perspective, this is my first sentence in my paragraph. This is my DI sentence in my paragraph. This is my last sentence in my paragraph. This is a sequential data input. And we use some embedding. It's the same as English or French, all embedded in terms of numerical variables. It's the same. I just embed ICD or CPT code into a numerical variables. It's nothing different. And then I do some positional encodings. Positional encoding previously tell me, okay, if this sentence in the beginning of the paragraph, if this sentence is towards the end of this paragraph, here the positional encoding just tell me, okay, if this visit is 5 years ago, 10 years ago, or just 1 year ago, or just last month, right? With all of that, you see a very clear parallel between what we are trying to do in digesting an EHR to natural language processing. And then this is the current attention model. That is the state of art. Kind of think about it as, I'm going to open it up, next slide. But from here, let's think about it as just a way to process vocabularies in a sentence or sentence in a paragraph, so that towards the end, machine can only read numerical variables, right? typically in the natural language processing, they need a huge layer of things on the top that they transform all those numerical variables back to the language output. But I don't need that. All I need is two variables, really. One is the propensity score estimate, one single scalar, and the other one is kind of an estimated the treatment outcome. So my decoder here, after processing, so think about this, machine digests all of this information into here. And in the real natural language processing, you need to revert that process and back into a natural language again. But I don't need that. I only need the machine digest or the algorithm kind of compressed information or summary statistics of the entire records, just using an engineering structure that is using the attention-based mechanism. So what is this middle layer attention-based mechanism? And that's in the central piece. The central piece of attention-based mechanism. So think about right here. I have a raw EHR. Okay. This is the same patient I. This is a date in the January 3rd. And here's another date in the January 31st. Okay. So this are two hospital visits of the same person. So this is like two sentences in the vocabulary in the paragraph, or think about it as two vocabulary in the same sentence, regardless of how you think it. First of all, let's make them into a numeric vector. Right? We look up some representations of the ICD, or look up some encodings of the CPD or a representation. So make it numeric. And how attention mechanism works is really, I know that there is a start token. I want to summarize my visit 1 and visit 2. What I do is I'm going to create from visit 2, looping through the WK, create a key of 2, create a value of 2, right? And same here, create key, create a value, all right? So basically, the visit level information gets summarized into key and values. And then I look at a special token right here, a query. I'm going to have the query multiply on top of the key to get how important it is each visit to my outcome. I'm getting way ahead. So the idea is I have my query, multiply the key, I have my value, and then essentially I have how important for the task is of visit 1 and visit 2. And then I weighted average of my visit 1 result and visit 2 result to get the sum, to get my overall numerical representation. So this is a matrix form for that. And this is basically a matrix multi-head version of that. I have my EHR output, make it a numerical variables. I have a start token, this is a cross attention, to look at how important. Think about this, a sequence data, but getting shake up so that it's perfectly mixed. Each records, each visit to the hospital will examine its neighboring or even remote, past or future records to look at how important is each visit and get a weighted average so that all information is well mixed up so that I could get efficient summaries in the context. And context is really the key of this multi-head encoder-decoder attention-based mechanism. So we are not only looking at one single visit, we are looking at the visits, hospital visits in the context of entire history. Could be in the past, could be in the future of all available data. Up to the point of clinical, up to the point of treatment assignment. So really, that's the central piece of this architecture is able to do is really talking about, digest the entire records as the input and output a propensity score. And when they digest the entire records as input, they perfectly match informations into the context so that it knows. And I want to share some quick simulation results, and I'll open up to questions. Obviously, I'm showing the simulation results. My method is called attention-based mechanism. There is another machine learning model that previously used in the natural language, the previous generation, LSTM, long short-term memory. And I also compare mine with some existing methods that do the painstaking featureization. All right, there are some linear and nonlinear methods. Think about this: some linear regression method, linear regression method, linear regression method, some nonlinear method. All right, tree-based method. And I look at think about that as absolute standard deviation, standard mean difference. The smaller, the better. I'm really looking at this table. The boldface is the best. The blue boldface is best scenario. So I'm able to tell that the latest generation. So first of all, the attention-based method and LSTM, raw data learning, is better than having to do the featureization and then build a linear or nonlinear regression model. That's the message number one. The message number two is among the attention and LSTM, it seems that I also simulate under different scenarios. It seems that attention model give the better performance, in different metrics. LSTM is better, slightly better here, but getting worse in the bias and 95% confidence interval coverage. And this is another important thing when we look at the causal inferences, when we look at the covariance balancing, and we can look at, the unadjusted covariance is really bad, and adjusted covariance balance, this entire area of features gets better covariance balancing after the propensity score adjustment, propensity score weighting. And another thing I want to emphasize, smaller scale model, scenario ABC, is the interpretability. All right. So because attention-based mechanism really also outputs the importance of each visit compared to the entire record, in the simulation, I can simulate some visits to be important, and I look at the attention weight of my of the model output, and it's very reassuring to see that the attention weight marked by blue is able to have peak on those important visits. Right? Think about the EHR. Some of the visits just there for flu or for some minor disease is not important for the very important cancer or diabetes disease that you are trying to study. And we're looking at with more than 4 peaks, different types of behavior in the simulation setup. The universal message is that there is some false identification right here, but we are able to pick the majority of the important visits out. And 1 minute on my real world applications, and this is still work in progress. And the idea is to have a retrospective study where we look at the type 1, type 2 diabetes characteristics of the youth and young adults, demographics, and looking at the causal inference in this setting, looking at the disease management, such as ambulatory clinic, outpatient lab, to the severe outcomes like emergency departments, hospital admission, so on and so forth. And right now, I actually have the first part of this descriptive analysis ready. However, the server is down and I wasn't able to get any data out. We are encouraged to keep all the data on the server. So whenever the server gets down, I actually wasn't able to copy that out. So no more demographic result, but we have some preliminary data talking about some age and gender distribution. Unfortunately, this just emphasizes that there's another piece of difficulties, which is enrollment gaps that we think our method will be able to handle as well by imputing the middle missing visits. And the results on the causal inference is really a work in progress. And already run a little bit off the time, and happy to take any questions.
Yeah, any quick questions? You know where to find Shihao if you have more questions, but if you have anything burning and quick, we can take 1 or 2 questions. Shihao, there is a question in the chat.
Oh, okay. Thank you. Ooh, when you are decomposing NPD tensor, my understanding that the model makes assumption that every patient has PDI relationships. Not necessarily. DI can be very different. And in this case, because it's N is number of study subjects, right? So N can be whatever. It can be large. We will build the output will be, think about the propensity score is going to be a vector of N. So N doesn't matter. It's the P by DI that you are mostly curious about. P here, think about it as dimension just 3. All right, you have an ICD code, you have a CPT code, and you have sometime a lab results. Sometimes ICD, you have ICD from 1 to 6. Right, so P is small dimension, but D can really be different. D can be, either from a patient with only 20 records to a patient that visits the hospital nearly every week that may have less around 100 records. That's something we also typically see. Okay, let me finish this one. And so really is talking about taking a table of P by DI and output one single scalar. So really, each patient I doesn't really have to have a similar PDI relationships. Yeah, and also we concatenate that by the obviously by the baseline characteristics that's completely concatenated on top of that. So hopefully I've answered that. And the second question is most frequent factors for positional encodings, like positional encodings, time visits, other important ones that frequently come up. Okay, so the important right here is we are looking at not an important factor, right? When you look at a fact table, your importance in terms of which feature is important. Now we are looking at by each patient. Each patient, they have multiple visits. So now the importance is in the fact that in the idea that which visit is going to be important. For example, if a patient visits the hospital 3 years ago for a liver failure, that is probably going to be important for his treatment assignment down the road and the treatment outcome down the road. And that's what we mean by important. It's not about, dosage, place, or one of the feature being important anymore. No, we no longer need a feature engineering, so we do not have an importance on feature anymore. It's becoming an importance on the on visit. Think about as a natural language processing counterpart. There are some important vocabularies in the sentence, but if you ask me, okay, is book an important vocabulary? But I don't know, because if book doesn't appear in this paragraph, this question is no longer meaningful anymore. It's more about the important vocabulary in the sentence. The a is not that important in a sentence compared to a more adjective or non-important verb, for example. Okay.
And we have another question. Are the most frequent factors for positional encoding things like time, dose, place, and visit?
Yeah, I already answered this just now.
Okay. Thank you. Well, thank you, Shihao. And probably you're gonna hear from our people over email. So that's it, right?
Yes.
Jeff?
Yeah. Thank you, everyone.
Thank you, everyone.
Thank you.
Bye.